Hey everybody, Mr. Bells here. This video is for Precalc A, section 1.1 on functions and their properties. We're going to discuss things like whether a function is bounded or not bounded, local and absolute extrema, whether it is a function, isn't a function, domains and ranges, where it's increasing, where it's decreasing, a ton of different stuff about functions and their properties. I'm hoping we can get through this one in under 25 minutes. We'll see on the stuff. Here we go. So, first off, what is a function? Well, when we talk about whether one variable is a function of another variable, let's say that I had something like this, y is equal to x squared. That means that for any value that I put into x, right there, whether it's a 3 or a 5 or a 6, that every time I put that 3, that 5, or the 6 into here, I'm going to get the exact same number out of here. Okay? So in other words, it's 1 to 1. For every one number I put in here, I only get out the exact same number here. So in this case, y is a function of x. However, x is not a function of y. Why is that? I could put a 9 in for y. I put a 9 in here. Then I know that I can get out a 3 or a negative 3 in this case going backwards on that. So both those numbers work. Okay, so in this case y is a function of x, but x is not a function of y. When we ask most of the time if something's a function, we're usually talking about y being a function of x, and we'll use something called the vertical line test. Vertical line test. Where if I graph this, y equals x squared, that looks like this. That means anytime I take a vertical line, that means it's only going to touch at the most one part of the parabola. Okay? Whereas, for instance, x squared plus y squared equals 16, that's a circle. We saw that last unit. I graph that, it looks like this. Now you can see that that vertical line is going to pass through two different points. So in this case, y is not a function of x. Likewise, x isn't a function of y. Because if x was a function of y, like we said, this wasn't the case over here, then we go horizontal line test, and here the horizontal line would go through two different points. It would also do it over there. Okay? So again, 1 to 1. That means a certain variable is a function of another one. If we can put in a number, and every single time you get out the exact same number. Okay, so domain and ranges. So domain is what goes in for the x for most of our stuff, and range is what goes in for the y. Or domain is what goes in, and range is what comes out. Those are all terms for it. Okay? Another word that they might use in the textbook is independent variable, independent, and dependent. Okay? So how do we know what something's domain and or range is? Domain means all the legal values that you can put in for this x. So I guess the question is there anything that I can't legally put in for x? And the answer is nothing. So okay, so your domain is all reals, and we can represent that like this with interval notation, negative infinity to infinity, all real numbers. There's some like funky R stuff, looks like that kind of in the textbook, where you can represent all real numbers that way too. Now the range are all the values that you can get out of this. So that means all the possible values for y. Well, considering the fact that x squared, because it's being squared, can only be a positive number, and that can never be negative, you can see that it will never get below -4. So the range goes from -4 all the way up to infinity. Looking just like that. So let me give you a quick little picture on this. X squared minus 4. Y equals, clear that out. X squared minus 4, and I go ahead and hit graph. And you can see domain means, is there an x value all the way over here? Yep, because the parabola is going to get really, really wide. So it's going to touch x values way over here, and it's always going to touch an x value. It's always continuous along that. However, y values, that's the range. It never touches my finger down here. In fact, it doesn't touch at -10 or negative infinity if I go down, or -9, -8, -7, but look, it touches at -4, and it will have y values. In fact, it'll have y values in 2 different locations going up for those things. Are we good? Okay. It's the same y value at those 2 different locations, but it's a y value nonetheless. So that's why the range, the possible outputs, the y's, go from -4 to infinity. Now over here, this one's going to look a little bit different. I'm going to go ahead and graph this one first so you can see this. So y equals, and clear, so I have to do 4 divided by, and I got to put big parentheses here around the entire denominator, so almost like there's an extra set here. So, and then parentheses x minus 6, close parentheses, parentheses x plus 2. Then you're going to see this. You might remember this from data A in terms of rational functions, but if I go ahead and graph that, you're going to be like, oh, look, there's a weird heartbeat looking thing, right? So it looks like domain, those are the x's, right? I have x's all the way over here. You can't see it, but it goes down and it's really close to touching. That's called an asymptote, really close to touching here, but doesn't touch. And then all of a sudden there's no x here and there's no x here. So the domain basically is all reals except x cannot equal 6 or -2. And you're like, how did I know that, 6 or -2? Well, right here you can see that if I put 6 into the denominator, 6 minus 6 is 0, and 0 times anything is 0, so then I have division by 0, so that's why right here at 6, it's gone. It's gone. There's technically a vertical asymptote right there, so that's not part of the domain. So how would I write that if I was doing interval notation? So I know that it's -infinity to -2, union -2 to 6, union 6 to infinity. That's the domain. That's all of that. The range, on the other hand, is all the possible y values. So you can see there's y values that head all the way down, right? And y values that head all the way up. The only place the y can't be is right there. We can't ever have a y value of 0. That's impossible. There is a horizontal asymptote going all the way across. So the range is -infinity, 0, union 0, infinity. Okay? So the range is everything that exists except for 0. I can't get a 0 out of this because there's no values for x's that will make this fraction become 0, because 4 divided by nothing equals 0. That's why it doesn't matter what the x's are. Okay, so that's domains and ranges, and hopefully enough stuff that we talked about during class will help offset anything that you didn't get from this video. Okay. So continuity, what does continuity mean? Is there such thing as removable? So continuity means this. So let's say that I had a graph that was going like this. This one's continuous. It doesn't break, it doesn't stop, it doesn't do anything. But yet we just saw one of these things, right? This one isn't continuous, right? This branch goes towards -infinity and all of a sudden it pops up over here. So there's a break going on. It's discontinuous at that thing. There's nothing there. And then what we say is this one specifically is non-removable. We can't fix that thing. However, there is such thing as removable discontinuity. And what's going to happen is I'm going to show it to you on this one right here in just a second. But that's going to be a function that looks, and I'm not going to draw this one specifically, but it's a function that looks like it might be continuous, but there's a tiny little hole in the graph someplace. So there's a little gap, only a gap for one number. Like if I go a tiny 10 billionth of an inch to the right and a tiny 10 billionth of an inch to a left, there's a number there, but there's no number at that specific location. Okay, so there's a hole, and that's what we consider removable. Okay, so non-removable, that's like an asymptote. Removable, that's where there's a little hole in there. Okay, so why does this thing give us a hole? Watch real quick. So I go to my y equals, and I'm going to clear all that out. So I'm going to do parentheses x minus 5, close parentheses, divided by, remember, big set of parentheses, and then, I don't have two things. I can just do this in one spot here. Oh, dumb. X minus 5, close parentheses, divided by parentheses, x squared plus 2x minus 35, and close parentheses, and graph. And you're like, I don't see the hole. Looks like it's pretty continuous. And let me show you this on here. So zoom, format. I'm going to turn my axes off right here. Turn my axes off, and then hit graph, and you can see it. It looks like it goes on forever, right? That there's no issues right there. But I'm going to say that there actually is an issue right over here at 5, and you can't see it right now, but there's going to be a hole over here at 5. So what I'm going to do on my window is I'm going to have my x min at 4.9 and my x max at 5.1. I'm going to just check this out and see if there's anything that you guys can see here. Did you guys see that? Look at that. Pixels all the way along, and then poof, right there. There is no pixel. Okay, there's no pixel at x equals 5. There's a hole. So this one is a discontinuous function, but it's removable because there was a hole. Okay, now the question is, what the bleep? How did that happen? Why did that come up on there? Is it just a mess up on my calculator or not? It's not, and here's where holes come from. And I'm going to go over it in detail in the back part of this thing, but here we go. If I factor this bottom thing out, it becomes x plus 7 times x minus 5. And then you can see that I have a factor of x minus 5 upstairs and downstairs. Those are identical. And then that means that they are removable. So, oh, look at that. I can remove that factor. And what would have given me a 0 right there? But x equals 5. And that's why there's a hole on it. And if you clicked on Desmos and tried it, Desmos actually shows you a hole just like this little sucker right there. You just got to get close to that. So if you want to type that into Desmos right now, you can do that. Good deal. Okay. So next, we're going to talk about extremas. So extremas are when functions have high points or they have low points. And that's kind of important when we start looking at functions and applications, especially we're looking at when we want to know when a thing is going to maximize or minimize in the business world and the medical world and whatever those situations are. So we're going to look at extremas. Okay, so this function right here does not have any absolute extremas. It goes towards infinity and it goes towards negative infinity. So there's no absolute low point or no absolute high point. However, it does have some local ones. So this would be considered a local maximum, and this would be considered a local minimum. So a local max and a local min. Because over a certain stretch of the function, it reaches a high point, or it changes between increasing and decreasing at that location. Okay, where this function over here is extrema, you can see that this one right here, not only is it local because it changes over a small value, but this one's also an absolute minimum, which means the function will never get lower than that point right there. Okay, this would be a local max, this would be a local min. This one does not have an absolute maximum. So if I was trying to, maybe this was product growth for some reason or something, and I said, hey, is there ever going to be a maximum amount of situation for this particular variable set. And you'd be like, no, it goes to infinity when I go negative, it goes to infinity when I go positive. However, it does have a minimum. Okay, it does have a minimum. Okay, increasing versus decreasing. Okay, so when we're looking at this, when we're talking about whether a function's increasing or it's decreasing, we're looking at what the function does. What the function does from left to right. Okay, so we're going to look at the x's. We're going to look at the x's. So what is the function doing as we're moving from negative infinity, xy is left, to positive infinity, xy is right. So let me do this one right here. So I know the function looks like it's going down right here. That doesn't mean it's decreasing. As I'm moving from left to right, this function's actually getting bigger, and it's increasing until it hits this point right here. And then from this point right here to this point right here, you can see from left to right, it's decreasing. And then from this point right here, all the way to the right, it's increasing. So when we're talking about increasing or decreasing, we're talking about the x values setting the boundaries. Okay, so again, we tell whether it's increasing or decreasing based on what the y's are doing, right, if it's going up or down, but we discuss it based on the x's setting the boundaries. So for instance, on this one right here, let's say I'm going to drop this straight down, and this was at -3, and I'm going to drop this straight down, and this was at 2. Then this function would be decreasing, are you with me? Would be decreasing from -3 all the way to 2. And I don't honestly care if you want to put brackets or parentheses at this point, whether or not you're going to include that point or not include that point, because it technically is not increasing or decreasing at that thing. So I'm going to use open parentheses, but if you want to use brackets, I don't really care. Okay, so where is it increasing? It's increasing from negative infinity to -3, and it's also increasing from 2 to infinity. Okay? However, at 2 and at -3, it is not. And in fact, if we took the tangent lines at this point, you would see that the two tangent lines, or the slopes of the tangent lines, would be 0 at those two things. There's nothing going on. Okay, boundedness, things can be bounded above or below, and really all that's talking about when we're talking about boundedness is there maximums or is there minimums. So let's take a circle. So if I was to graph a circle, this one's bounded above because it never gets above a horizontal line, and it's bounded below, it never gets below a vertical line. And if I take this one right here, this parabola, this one's bounded below because there's no part of that function that goes below this line. There's a boundary down there below it. If I took this parabola, this one's bounded above, and let's take this real basic simple one, y equals 2x plus 3. That looks like this, right? Looks like a line. This one's not bounded at all because there's no horizontal line that is completely above it. Like if I put it here and you're like, well, that's above it. Well, no, this line goes on forever and keeps going up and up and up. So there's nothing that can bound it on the top side, and there's nothing that can bound it on the bottom side. So hopefully that was good for you guys for boundedness. We good? Okay. So we're getting close. We got two more topics that I want to be able to talk about right now. One's even functions versus odd functions. Okay, so this is going to be a little weird, but I'm going to be okay. I'm going to hopefully be okay with this. So even function and odd function. Now, you could look at this and go, hey, well, that's even, and hey, that's odd. Great, good deal. So, and that's true. This is even, and this is odd. But what it means is this, that if I put in 3 or -3, that I'm going to get out the same number, 9 in this case. So even functions have symmetry over the y-axis. So whether you put in positive x, okay, whether you put in positive x or negative x, they're going to equal the same y, okay? Odd functions, like y equals x cubed, like this, if you put in x, you're going to get out y, but if you put in negative x, you're going to get out negative y. So for instance, in this case, 2 comma 8 is a part of this, and -2 comma -8 is a part of this, okay? So this is where it gets weird. Y equals x squared plus 7 is still an even function, but y equals x cubed plus 7 is not an odd function. You're like, wait, what? I can add 7 to this and it's still even, but if I add 7 to this, it's not still odd. Well, the x squared, again, to be even, needs to be symmetrical about the y-axis. So if I do x squared plus 7, that's just a parabola that's been shifted up 7, and it's still symmetrical, so that a given x will give you a certain y, and the opposite of x will give you that same y. However, an odd function has to have symmetry around the origin. So as soon as I move this up here, like that, I move that up 7, now it does not have rotational symmetry about the origin, right? So if this point was 2 comma 15, it's -2, -15 is not on this, right? -2, -15 is here, and that is going to be out this way, okay? So I want to make sure you don't just assume even degree, even, oops, sorry, my lights just went out, there we go, and odd degree, odd. It's based on its symmetry, good deal, and we could have things like this, x equals y squared. This is not a function at all, right? It's not a function, or at least y is not a function of x. X is a function of y, but y is not a function of x because it fails the vertical line test, yes? But this one does have x-axis symmetry, and we'll talk about things that are functions or relationships, or whether they have y-axis symmetry, origin symmetry, or x-axis symmetry. These two being reflectional symmetry, this one being rotational symmetry, as we go through some of the stuff. Okay, hopefully that's good. Okay, so last big thing, we're going to talk about VAs, HAs, XINTs, YINTs, and holes, all on this function right here. So vertical asymptotes, places that don't exist vertically because of a certain thing. Horizontal asymptotes, places that don't exist horizontally, or at least not as it heads towards infinity. X-intercepts, where it crosses the x-axis. Y-intercepts, where it crosses the y-axis. And holes, those things that we talked about right back here, right? Remember that one right there? Hole. Okay. So you have to be able to do all 5 of these things. And yes, we did those in data. But again, some of you had it at different times, and with COVID and all the stuff that happened during this time, who knows? The video right now currently is being made in 2020, and hopefully we will be back in person once you guys come back in January. So here we go. Let's do all this stuff. So what are some of the things that I can do in the beginning? When it's in this form, there are 2 things that I think I can do pretty easily, and that's I can tell what my y-intercept is, and I can tell what my horizontal asymptote is. I can't find these, this, or this. I can't find the vertical asymptotes, the x-intercepts, or the holes until I factor this thing, okay? But I can find the horizontal asymptote and the y-intercept pretty easily. The y-intercept is when x is 0, So I want to do that right now. So plug 0 in for x. You'll see that this x squared, and that x all go poof. And I'm left with a 6 over a negative 4, which reduces to 3 over negative 2, or negative 1.5. Okay, so one more time. I plug in y-intercept is when x is 0, so I plug in 0 for x. All those x's drop out, and I'm left with 6 over negative 4, which reduces to negative 1.5. So my y-intercept, this graph hits the y-axis at 0, negative 1.5. Okay, horizontal asymptotes, and this is going to be a pretty quick rundown from this, but hopefully you guys remember this from data A. I look at the highest degree term in both the numerator and the denominator. If they are the same degrees, then I look at their coefficients, and their coefficient here is 1, and their coefficient here is 1. So my horizontal asymptote is y equals 1, because 1 divided by 1 is 1. And if we were to graph this whole thing, you'd be like, whoa, look at that. It really does have a horizontal asymptote at 1. Well, why is that? Here's a quick little thing. Horizontal asymptotes occur when x is head towards infinities. So pick, I don't know, like a big flippin' number for x, like a billion. Okay, do you agree that when I plug it into x squared, a billion squared is going to be a lot more powerful than 5 times a billion or a little number 6? Yes, most powerful. Most powerful down here. Okay, so if these two things, as x approaches infinity, these two things here and this negative 4 here, have no bearing on it, we only have to look at the most powerful parts. And a billion squared over a billion squared is same thing over same thing, or 1. Now, quick little check. If it was like this, x over x squared, then my horizontal asymptote would be y equals 0, because a billion over a billion squared, this is getting bigger and bigger and bigger, and anything divided by something much, much huger than that is going to approach 0. Again, this fraction can never equal 0, but the horizontal asymptote, the place that it can't touch, the place that it gets closer and closer to, can equal 0. However, here, x squared over a regular x, when the denominator is bigger, then there is no horizontal asymptote. When the numerator is bigger than the denominator's degree, there's no horizontal asymptote. Technically, it will be considered something called a slant asymptote, and we'll deal with that much later in this chapter. Okay, so there's a quick little rundown on it. Now I'm going to show how to get these three things by factoring this. So factoring the top, I get x plus 2 times x plus 3. Factoring the bottom, I get x plus 2 times x minus 2. Good deal. I can see that this cancels this, and remember just a little while ago we said if we have the same factor upstairs as downstairs, it is removable and it leaves a whole. Good deal. Whole at x equals negative 2. So where's my whole? When x equals negative 2. Technically, I can't put that as a coordinate because there is no corresponding y value because there's nothing that exists there. Okay? So, no, right? Technically, this is negative 2 comma undefined. There's nothing there. There's nothing there. Okay. So now I just have to find my vertical asymptote and my x-intercept. Well, my vertical asymptote is what's ever left over after I've removed my holes. And my x-intercept is from whatever's left over in the numerator spot. So verticals goes from the denominator, x-intercepts goes from the numerator. So where's my vertical asymptote? This value to make this a 0 would be 2. So my vertical asymptote is at x equals 2, positive 2, because 2 minus 2 is 0. 0 times 0 is, 0 times anything is 0. Division by 0 is undefined. That's why nothing exists at x equals 2. My x-intercept, however, is different. That's the value that makes this thing equal 0, right? It's what values for x's give us a 0, and that would be negative 3. Okay? So hopefully that's good and where all those came from. Again, the only way I can get 0 out of this function is I do this. Now, what I would want you to do is actually check this out right now, and I can't. exactly pull it up on Desmos as easily, and the picture will look okay. But if you graphed right now in Desmos, and I'd really want you to do this, x squared plus 5x plus 6, division x squared minus 4, and check to see if there is a vertical asymptote at 2, a horizontal asymptote at y equals 1, an x-intercept or where it crosses the x-axis at -3, a y-intercept or where it crosses y-axis at 0, -1.5. And if you look closely enough where x is equal to -2, you would see a hole is there. Awesome. Hope this video has been helpful to you. If you're watching this video, awesome, and you want to send me an email right now that says, I don't know, let's go green penguin, I don't know, but give it a shot. We'll get you some extra credit for the first 5 people that do that. Just because I want to make sure that people are actually watching these things. Good deal. We'll talk to you later.